Up until now, we've seen two numerical methods for ordinary differential equations: the explicit Euler method and the implicit Euler method. In this video, we're going to see much more than those. We are going to take a look at a few variations of the Euler method, so to speak. And I believe now is the perfect time to do that, because earlier in this class, we have introduced the concept of local discretization error. The basic takeaway was that if we understand the local discretization error of a numerical method, then we also understand the global discretization error. Once we understand the local discretization error, we can apply our theorem and get the global discretization error for free, so to speak. In that spirit, this video consists of two parts. First, we take a look at a few numerical methods, specifically the explicit midpoint method, the implicit midpoint method, the Crank-Nicolson method, and Hoyne's method. So we get to know 4 additional numerical methods. In the second part of the video, we calculate the local discretization errors for each of these numerical methods. As you recall from the last video, the explicit Euler method and the implicit Euler method have local discretization errors which generally converge quadratically to 0 as the step size goes to 0. That is, our estimates for the local discretization errors are some multiple of h squared. The numerical methods that we investigate in this video generally do better. Their local discretization errors converge cubically to 0 as the step size goes to 0. So when we fix some step size h, then these new numerical methods will generally perform better than the explicit or the implicit Euler method, in the sense that we get better approximations to the true solution. That being said, their algorithms are more complicated, and also the theoretical discussion takes more effort. Okay, we already know the explicit Euler method and the implicit Euler method, and now we're going to see some of their friends, namely the explicit midpoint method, the implicit midpoint method, the trapezoidal method, which is also known as Crank-Nicolson method, and Hoyne's method. These 4 new numerical methods are more complicated than the explicit and the implicit Euler method, but they also have better performance in practice. All these numerical methods are designed to approximate the solutions of Cauchy problems. So let us fix that U is a solution to U prime of t equal f of t u of t with initial condition u of t naught equal u naught. As a preparation, let us briefly revisit the explicit and implicit Euler method and their connection to integration. For the explicit Euler method, we recall that u at time step tk plus 1 equals u at time step tk plus the integral of u prime of s taken from tk up to tk plus 1. Of course, unless we already know the solution u, we cannot compute this integral. But we observe that we can approximate this integral by taking the point value of u prime at tk and multiplying it with tk plus 1 minus tk, the length of the interval. In that sense, we approximate u tk plus 1 by u of tk plus tk plus 1 minus tk multiplied with u prime at tk. Okay, now we use the differential equation in order to substitute u prime. So we can also write u at time tk plus 1 is approximately u at time tk plus h times f of tk u at tk. This last approximation is our inspiration for defining the iteration formula of the Euler method. Having computed an approximation uk of u at time tk, we compute uk plus 1, an approximation of u at time tk plus 1, by setting uk plus 1 equal uk plus h times f tk uk. Similarly, we can come up with a motivation for the implicit Euler method. So again, we have u tk plus 1 being equal u at time tk plus the integral of u prime from tk up to tk plus 1. This time, we approximate the integral by taking the point value of u prime at the right end of the interval at time tk plus 1. Again, substituting the differential equation, we get the approximation that u at time tk plus 1 is roughly the same as u at time tk plus h times f at time tk plus 1 and u at time tk plus 1. That's another approximation of u at time tk plus 1, and it serves as an inspiration for the implicit Euler method. Having already defined uk, the approximation of u at time step tk, we compute uk plus 1, the approximation of u at time step tk plus 1, as a solution of the equation uk plus 1 equal uk plus h times f tk plus 1 uk plus 1. Again, this is not a straightforward computation at each time step, but in general, we need to solve a system of equations, most likely a nonlinear system of equations. As you can tell up to now, the starting point for the explicit and the implicit Euler method is to think of an approximation for this integral of u prime. For the explicit Euler method, we take u prime at the left end of the interval, and for the implicit Euler method, we take u prime at the right end of the interval, and then weight these by the interval length. So this leads us to the domain of numerical integration. The new numerical methods that we are going to see are based on choosing more accurate approximations of that integral, which then hopefully lead to more accurate approximations of the solution of the Cauchy problem. One idea is to use the midpoint rule to approximate the integral. One way of doing that is known as the explicit midpoint method. So again, we have the integral formulation of the ordinary differential equation. U at time tk plus 1 equals u at time tk plus the integral from tk up to tk plus 1 of u prime. Now let's approximate this integral of u prime by the midpoint rule, which means we take the value of u prime at the midpoint of this interval and multiply that with the interval length. So u at time tk plus 1 is roughly the same as u at time tk plus the length of the interval, tk plus 1 minus tk, multiplied with the value of u prime at the midpoint of the interval, which is u prime at tk plus 1 over 2. Okay, let's go by that. And we use the differential equation in order to substitute u prime. So we get that u at time tk plus 1 is roughly the same as u at time tk plus h times f at time tk plus 1 over 2 and u at time tk plus 1 plus tk over 2. We would like to use this approximation to define a numerical method. Now, but in contrast to the Euler method, the explicit Euler method, this is not yet ready to go because we do not know u at time tk plus 1 over 2. So in order to make this method useful, we need to approximate u at the midpoint of the time interval. And that can be done, for example, by the explicit Euler method. So we make another additional approximation, namely we say that u at time tk plus 1 over 2 is roughly the same as some value which I call uk plus 1/2. That's just notation. And uk plus 1/2 is defined as uk plus h over 2 times f tk uk, where uk is the approximation that we have obtained in the previous iteration. To make this formula a bit more helpful, let us write tk plus 1/2 as an abbreviation for tk plus h over 2. So tk plus 1/2 is just the midpoint of the interval. So what we then compute in the end is, suppose we already have uk, we define uk plus 1 as uk plus h times f at tk plus 1/2, uk plus 1/2, where uk plus 1/2 is defined as above. So what we actually compute is uk plus h times f tk plus 1/2 and uk plus h over 2 f tk uk. That is the explicit midpoint method. So to summarize, the idea of the explicit midpoint method is that I approximate the integral by the midpoint rule from numerical integration. And since I do not know u at the midpoint of the time interval, I make an additional approximation using the explicit Euler method. So I take the explicit Euler method with half of a time step and use that value to feed it into the midpoint rule. That is the explicit midpoint method. The explicit midpoint method has a friend called the implicit midpoint method, and that one is defined by not using the explicit Euler method in this subcomputation, in this auxiliary computation, but instead using the implicit Euler method. So the implicit Euler method looks very similar. So we still have the integral formulation of the Cauchy problem. We still use the midpoint method to approximate the integral by taking the value of u prime at the midpoint of the time interval. Again, we substitute u prime using the differential equation. And just as before, we need an approximation of u at the midpoint of the time interval to make this idea useful. So we still need to define an approximation uk plus 1/2 of u at time tk plus 1 over 2. However, uk plus 1/2 in this case here is not defined using the explicit Euler method, but this time, let's just use the implicit Euler method. Because why wouldn't we? So we define uk plus 1/2 as a solution of the following equation: uk plus 1/2 equal uk plus h over 2 f at tk plus 1 over 2 uk plus 1/2. This is an auxiliary computation, and we solve this equation for uk plus 1/2, just as we do for the implicit Euler method. Again, let us abbreviate tk plus 1/2 for tk plus h over 2, which is the midpoint of the time interval. And so, having obtained uk plus 1/2 in this auxiliary computation, we just straightforward define uk plus 1 equal uk plus h times f at time tk plus 1/2 and uk plus 1/2. So at each iteration, having already obtained uk, I first use the implicit Euler method with 1/2 of a time step to obtain uk plus 1/2, which is an approximation of u at the middle of the time interval. And then I feed this into the midpoint rule to obtain my next iteration, uk plus 1. All right, the midpoint method is fun, but the trapezoidal method is even better. Using the trapezoidal rule to approximate the integral leads to what is known as the trapezoidal method, or alternatively, the Crank-Nicolson method. Okay, let's get back to the integral formulation of the Cauchy problem. So u at time tk plus 1 equals u at time tk plus the integral from tk up to tk plus 1 of the derivative u prime. This time I approximate the integral by the trapezoidal rule. So you remember that the trapezoidal rule is defined by taking the value of the integrand at the left and the right endpoint of the interval and summing them up with weight the interval length over 2. That leads to the following approximation, namely u tk plus 1 is roughly the same as u at time tk plus 1/2 times the interval length tk plus 1 minus tk times u prime at tk plus u to prime at tk plus 1. Similar as before, we use the differential equation in order to get rid of the derivatives u prime here. So u at time tk plus 1 is then roughly the same as u at time tk plus h over 2 multiplied with f at tk u tk plus f at tk plus 1 u tk plus 1. We use that approximation in order to define a numerical method. So let's suppose I've already computed uk, which is an approximation of u at time tk, and then I define uk plus 1 as a solution of the equation uk plus 1 equal uk plus h over 2 times f tk uk plus f tk plus 1 uk plus 1. This equation defines uk plus 1 implicitly, and at each iteration step we need to solve it for the unknown uk plus 1. The Crank-Nicolson method is an implicit method based on the trapezoidal rule. At each time step, we need to solve a possibly nonlinear system of equations. And because implicit methods, for all their merits, come with some theoretical and computational complexity, we are also interested in an explicit method based on the trapezoidal rule. The most important example for that is Hoyne's method, which was developed in around 1900 by the German mathematician Karl Hoyne. So this starts off very similar as the Crank-Nicolson method. We have u at time tk plus 1 equal u at time tk plus this integral of u prime over the time interval, and we approximate this integral then by the trapezoidal rule. Just as before, we substitute u prime using the differential equation. And so we have the approximation u at time tk plus 1 is roughly the same as u at time tk plus h over 2, and then multiplied by the sum f tk u tk plus f tk plus 1 u tk plus 1, just as before. As an inspiration for Hoyne's method, we then apply an additional approximation. Namely, we say that u at time tk plus 1 is roughly the same as u at time tk plus h times f at tk u tk. These two approximations lead to the following numerical method, where each iteration consists of 2 computation steps. So let's suppose I've already obtained uk, an approximation of u at time tk. Then first I compute zk plus 1 equal uk plus h times f at tk uk. In other words, I first apply the explicit Euler method. Now, that value, zk plus 1, is an approximation of u at time tk plus 1, and I put this into the trapezoidal rule. And then I define uk plus 1 equal uk plus h over 2 multiplied with f tk uk plus f tk plus 1 zk plus 1. Each iteration step of Hoyne's method consists of 2 straightforward computations, and then uk plus 1 is my approximation of u at time tk plus 1.